So the geometry of the set of a visible solution. Remember the visible solutions for a linear programming problem. All vectors from say Rn such that the constraints given by a matrix A times X less than or equal B, or equal in the canonical form. Less than or equal is the standard form. Replacing this with equal gives will be a canonical form. Okay. So the matrix here represents a set of constraints, right? One of them may look like one constraint looks like A transpose times X less than or equal BI. You remember B, the vector B is in the set is in okay, we need to specify the dimension actually. Okay, as we have seen before, this is the same as the number of the the number of the rows in the matrix A. So let me go there. So this is a review. So the matrix A, if it is if it has m rows and n columns, and then this is X and it belongs to Rn, as we said. Now this equals or less than or equal, remember this, B1, B2 all the way to Bn. Okay, and this is X1, X2 all the way to Xn, and this starts with A11 all the way to AM1, A12, AM2. And this must be AN1. Okay, AMN, sorry, A1N. You have seen this matrix before. Okay, and so and this will become M, and now we go back and say this is in Rm here. Okay, so one of the constraints when I said one of these, it might be one of the rows in here, one of the rows multiplying this column. Say it is the ith row. The ith row will give us, will be less than or equal Bi. Good. So okay, let's go back to where we were. So assume we have two solutions, visible solution. Okay, which means they satisfy this equation here, the equality or equation. Now the idea here, any point on the line segment joining these 2 points is also a visible solution. So what is the idea here? So if we have x1, a visible solution, satisfy the above things, and another point x2, also a visible solution. Now what we are saying here, that if we take any point between the line segment containing x1 and x2, then that other point, call it x, is also a divisible solution. Okay, this is what we want to show. Okay, this is what we want to show. Let us start now. How we describe the line segment joining x1 and x2? We must give it some equation. So this line from here to here, how we give it that equation? Actually, it is of this form. So any line, any point on the line segment between x1 and x2 comes as lambda, some scalar, times x1 plus 1 minus that scalar times x2. Now lambda is between 0 and 1. الidea هنا this coefficient and this coefficient, they can be anything between 0 and 1, but their summation must be 1. So we may say we want the line segment, we can describe it the set of all points in Rn such that these points come this way. You may say C1 x1 plus C2 x2, so that C1 plus C2 equals 1. Okay, now you may replace lambda with C1 and lambda minus 1 with C2. Okay, so the line segment joining two points is described by lambda times the first point plus 1 minus lambda times the other point, or C1 x1 plus C2 x2, where C1 plus C2 are scalars and their addition equals 1 exactly. So this is the line segment joining the 2 points. Now if we start with, for instance, if we choose in here, if we choose lambda equals 0, then we get x1, right? X2, sorry. We get x2. Substitute 0 for lambda, we get x2. Here, we are here. Well, lambda equals 0, we are here. Now substitute lambda equals 1, then we get x1. So lambda equals 1 bring us here. Now what if we substitute lambda equals 1/2? That will be 1/2 x1 plus 1/2 x2. This will be in the middle. One half x1 plus 1/2 x2, and this will be in the middle here. Okay, now let's have more fun. Let us write more points. What if we make lambda equals 1/3? Then we get x to be 1/3 x1 plus 2/3 x2, and this point will be like here, 2/3 of x2 and 1/3 of x1. So this point will be here. Okay, but if we choose lambda to be 2/3, then x, let me use another color for that because my graph is getting messy. If we use for instance lambda equals 2/3, that will give x equals 2/3 of x1 plus 1/3 of x2, and this will be kind of here, closer to x1 than to x2. Okay, So what value, whatever value you choose for lambda, and then substitute, multiply lambda by x1, and then multiply x2 by 1 minus lambda, add it together, you get a new point, and that new point is on the line segment, okay, between x1 and x2. So x1 and x2 are called the endpoints, and the interior points consist of any point inside the line segment, okay. So this is the line segment. This is how we describe line segment connecting two points. Now what do we need it for? Actually, for the following definition: a subset S of Rn is called convex set if for any two distinct points x1 and x2 in S, the line segment joining x1 and x2 lies in S, okay, and the line segment is given this way. So that is S is convex if whenever x1 x2 belongs to us. If x1 and x2 belongs to us, then the line segment between them must also belongs to us. But the line segment consists of all combination lambda x1 plus 1 minus lambda x2. So any such combination must also belong to us, okay? So the set S is convex if we choose any two, if for any pair of elements from S, the line segment, any pair of elements x1, x2 from S, the line segment joining them is in S also, okay? Like, to make that clear, let me show you a set which is not convex. For example, this set S is not convex. Why? Because we have 2 points. We can choose this to be x1 and this to be x2. Now it says here, if the line segment joining x1 and x2. So let's make a line segment joining x1 and x2. This is the line segment. Oh, it's not inside S. It's not totally inside S. That's why it's not convex. Okay? And now this is important to understand that this belongs to S. This belongs to S, the whole expression. If you give me x1 and x2 from S, x1 and x2, then lambda x1 plus 1 minus lambda x2, whatever lambda is, that resulting thing must be inside S also, and lambda between 0 and 1. So this is the definition of convex set. Let us see some examples, some graphs of convex and non-convex sets. So these are graphs of convex sets. As you see, the shaded area is convex wherever 2 points we take in this S and join them, then the line will stay in there. And same thing for this triangle. Choose any 2 points, these 2 points, or any 2 points you choose. Make a like segment between them. The resulting line segment will be inside S. And this is another kind of convex. These are called bounded convex sets. The ones in here are called bounded convex sets. These ones are convex, but they are not bounded. Like for this one here, if we have such a line, it is infinitely line, and then we take the whole area, the half space. You remember that when we define a half space, like if we are in 2 dimension, x and y, and then we take some line, okay, and if we assume that's bigger than or equal some k, which means I think k is positive, not this one, because if we choose the 0 0, so I will say less than or equal k. Okay, less than or equal k. It will be this half definitely. So it is a half space. Remember that it is closed half space, right? And it is a convex set. It is convex. So this is what we mean here. This is another one, but the line here is this is constrained by two lines. The positive quarter or quadrant of the xy coordinate. In here, if we have one line and another, and this goes to infinity, and then this is a convex set. That means, like, if we take another line here, and this is say this is dx plus by is less than or equal some k2, for example. This is k1. So this is also another half space, and it is a convex. Now what we are saying here for this example, like if we have that part intersecting intersecting the two half spaces, and then we get this area. So it is convex also, which is similar to that one. Okay, and in three-dimensional case, if we take the xy plane, and it is a convex set. Okay, so half spaces are convex sets. Other examples of non-convex sets. Now, any one of these is non-convex. This is clear. This is clear here. Why it is not convex? x1 and x2, the line segment joining them is not contained entirely in the area, and this one is not convex. These 2 points, the line segment between them is contained in the area, but if we make another choice, say this is x1 and this is x2, then the line segment must be this way, and it is not contained in S. So the convex set says for every pair of points, the line segment joining them must be always also there, which means to say that a set is not convex, then it is enough to find one pair of elements with the line segment between them not contained in S. So one pair only. Okay, so we are done with the definition of convex. So let me see here. This is not convex for any one of these. Let me go back there. I called these ones to be bounded convex sets, but the ones below here, they are convex sets. Every one of them is convex, but not bounded, because you can see them, every one of them just continues forever from this side, and this one continues forever from this side. So they are not bounded from, each one of them is not bounded from one or two sides. Okay, so actually we will come back to what we mean by bounded. A convex set would be bounded if we can contain it in some triangle. And how we define triangle in Rn, a box or a triangle in 2 dimensions, and a box in multi-dimension. We will come back to that. Okay. So we know what convex means. And let's take some theorems for a quick. We will not prove them because they are obvious. Okay, closed half space is a convex set. Okay, I said we will not prove them, but let us give it a proof. You must remember what we mean by a closed half space. Okay, so this closed half space consists of all points x belongs, say, to Rn, such that what? A transpose time x is less than or equal or greater than or equal some bi, let's say, right? So half space consists of all the points that satisfies some inequality. Remember that? If we are in 2 dimension, then this equality can be represented in a line, and then we take one of the sides of the line. This is the closed half space. If we are in 3 dimension, then we have a plane, and then we take one side of the plane. This gives a closed half space in 3 dimension. In 4 and higher dimension, we cannot imagine them, but it is an equation of an inequality with n variables, and the set of points that satisfy this inequality is called the half space. And we write this inequality this way: A transpose, a vector, times x is less than or equal some number bi. Okay, now we want to show this set is a closed half space. So let me do this. Let me delete that. I want more space and bring this theorem by its own. I said the proofs are obvious. They are, but let us write it down so that we get used to that notation. Okay, so that we get used to the notation. Okay, oops, what did I do? Okay, now let's work the proof. Let S be a closed half space. Okay, then, as I said above there, S consists of all points that belongs to Rn, such that A transpose x is less than or equal bi. For some vector A transpose and some value bi. Okay, good. Now we want to show S is convex. Okay, now here you may say, but it's clear, why are you proving this? It is a line, then take one of the sides of the line. It is convex. Or a plane, take one of the sides of the plane. What about higher dimension? But the idea here, we want to get used to do proofs with convex sets. We want to use the definition we just introduced for convex set. So wanted to show that S is convex. What does that mean? That is, want to show that if x1 and x2 are 2 points in S, then lambda times x plus 1 minus lambda times x2, lambda times x1, 1 minus lambda times x2 also belongs to S for any lambda between 0 and 1. Good. So this is the line segment. So we chose 2 points from S, and then we want to show that the line segment joining x1 and x2, the 2 points, is also in S. So lambda x1 plus 1 minus lambda times x2 must also be in S. Okay? But remember that how an element can be in S. This will be in S if we show that what? This x belongs to S if it satisfies that. Correct? So we want to show, now let us give this a name x. So we want to show that this belongs to S. Okay? We want to show this belongs to S. How we show it? We multiply it by A transpose. Okay? And then we want this to be in S. So let's do it. Now, A transpose times X, we replace X where its expression lambda x1 plus 1 minus lambda x2. Now this is a multiplication of vectors, and do you know how to do it? And you know that lambda is a scalar. Remember, lambda is a scalar, so this will be simply lambda times A transpose x1. So take the scalar outside, multiply the vectors, plus 1 minus lambda A transpose x2. Correct? Okay. But we know that A transpose x1 is less than or equal bi, and also A transpose x2 is less than or equal bi. Why? But A transpose x1 is less than or equal bi, and A transpose x2 less than or equal bi. Why? Because x1 and x2 are from S, right? So they satisfy this. Okay, so if we go back, this will be lambda times in here bi plus 1 minus lambda times bi, and this means now we have bi multiplies by lambda and bi multiplies by 1 minus lambda. Add them together, this is bi. So we are done what we want to show. This is less than or equal that. So A transpose is less than or equal transpose X, and that gives X belongs to S, and then we are done. Okay? So we showed that. I want you to now understand what we have done. If we have x1 and x2 belongs to S, then lambda x1 plus 1 minus lambda x2 belongs to S. and so S is convex. Okay, good. Anyone has any question? Actually, this theorem was supposed to be proved by you as an exercise. Now another theorem here which says hyperplane is a convex set. What is the definition of hyperplane? Let me copy this here, this theorem here. So what is the definition of hyperplane? It is the very same thing in here. If this is S, it consists of all the points x belongs to Rn. So let me see if somebody is participating in me. So x belongs to Rn such that A transpose x equals Bi for some Bi. Good? So what is the difference? It was here for the half space, it was less than or equal, but for the hyperplane, it is equal. Okay? So hyperplane, the set of all points that satisfy a linear equality in n variables. So to prove this theorem, we just go back and change this less than or equal, wherever it is existed, to equal. And then we are done. The very same thing. Okay. Now, know if you are saying you want this note, you mean the slides, the empty slide without my writing. I sent them to you. Actually, maybe this part was missed, but you can copy it. I sent you these slides before, but it did not contain this part about convex sets. But I think you can copy it. I will not send it again because I have already done. Okay. Now the intersection of finite collection of sets of convex set is a convex set. This is another theorem. Intersection of finite collection of convex set is a convex set. This theorem says if S1, S2, all the way to SR are convex sets, then their intersection is convex. How you prove that? The proof must be very easy, right? You want to show that, let us name the intersection to be S. So want S to be convex. Okay, so how we do it? Let me write that for quick. Let x1, x2 belongs to S. What do we want? Want x, any x that can be written this way belongs to S, right? Okay, so let's go. How we do it? Okay, now since x1 and x2 belong to us, that means x1, x2 belongs to Si for all I. Good? But xi is convex. So lambda times x1 plus 1 minus lambda times x2 must belong to Si, because Si is convex, right? And this for all I. So this belongs to I for all I, and that will give this belongs to their intersection. S1 intersect S2 intersect Sn. Okay, and then we are done. So x that we have chosen belongs to S, where this is x belongs to S, and that gives S is convex. So the intersection of convex sets is also convex. Good? Okay. Okay, so two more results about convex sets, and then we go back to the idea of line segments joining 2 points to visible solutions. What about them? So we left talking about visible solutions. When we will be back to it. Okay, now we want to know, to give an example of convex sets. Okay, we want to give an example of convex set, one that you used to work with in linear algebra, which is the solution space of some of any linear system. Here we go. Let M be A, B, and N times N matrix and be a vector. Take all the solutions together. All the solutions. That means S equals all vectors in Rn that satisfy this system is convex. Good? So how to prove this? Again, I must do it for quick. x1, x2 belongs to S. That means ax1 equals B and ax2 equals B. Okay? Now notice A times lambda x1 plus 1 minus lambda x2 equals, let's multiply them. We can distribute, right? You know that from linear algebra. Distribute the multiplication of a matrix over a vector. And now take the scalar outside. So this is ax1 plus take the scalar, which is 1 minus lambda outside. This is ax2, but we know this is B and this is B, so we have lambda B plus 1 minus lambda times B, which is B. So what we got, this vector now satisfies this equation. A times this vector gives B, and that gives lambda x1 plus 1 minus lambda x2 belongs to S, and that gives S is convex. So actually there is nothing new. What I did here is nothing new. You learned from linear algebra that the solution space, see what I said, of a linear system space. I said given a linear system, take the solution which consists all of the vectors that satisfy the linear system, take these solutions and then you called it solution space. Space means if you take any two vectors from there and make a linear combination out of them, which means the first one multiplied with some scalar and the other one multiplied with some other scalar, the resulting will be in that space, which means the resulting combination is also a solution of the linear system. So the one you know is more general, because I said linear combinations of two solutions. I did not say the coefficient must add up to 1 as here, lambda and 1 minus lambda. So this is a special case of what you have learned. But the terminology here, saying that the solution space is a convex set, this is the new thing, only that terminology. Okay, the definition. تعريف فقط هو الجديد عليه. Okay, one last thing about convex set and then we go back to visible solutions. The convex sets that are bounded or unbounded, bounded and unbounded. We have seen it. Bounded, the bounded convex set is the one we can, bounded convex set is one that can be enclosed inside a rectangle. It is bounded, so ممكن نحطها في box. الريكتانجل كيف شكله؟ rectangle في ال RN مثلا في ال 3 dimension rectangle هو من هالنوع. تعميم rectangle في 3 dimension. So if this is x axis and this is y axis and this is the z axis, for example, then this rectangle says the x coordinate shall be between, for example, 0 and 0 and say some number, and the second coordinate between 0 and some other number, and the third coordinate between 0 and some other number. So this is A, maybe this is B, and this is C. Now this box you can move it into the space anywhere. So instead of that 0, you may say A naught, which is any element, B0, and C instead of this C0. So the coordinates in here you may use x1, x2, x3 instead of x, y, z. So this is the idea. Each variable or each coordinate is bounded by some interval. So this by some interval, the other by some interval, the other dimension by some interval, and so on. So this is a rectangle. So a convex set is called bounded if it can be enclosed some rectangle. If not, then it is unbounded. So good, okay. So we learned what convex set is and some theories about them. So let's go back to what we want them for. Okay. Assume x1 and x2 are feasible solutions for some linear programming problem, and that they satisfy some constraint given by A transpose time x is less than or equal B. Okay, so visible solutions because they satisfy some constraint, and let us call that constraint bi, some constraint. Okay, now let us take x to be some point on the line segment joining x1 and x2. Okay, so we are assuming that we have x1 say here, x2 say here, and now we are saying that let x be some point somewhere. So this is x. Okay, now we want to show that x is a visible solution. Now that means if I have two visible solutions, then any point on the line segment between these is also a visible solution. This is what we are saying. Is that true? How we show this is true? This is equivalent for showing that is A transpose X is less than or equal BI. Correct? So if we can do it. Okay. But note, this X shall equal, it is on the line segment between x1 and x2, so it is 1 minus lambda x1 times 1 minus, lambda x1 times 1 minus lambda times x2 for some value we choose, lambda, for some, that is between 0 and 1. So since it is on the line segment joining x1 and x2, then it must take that form. Okay, now we go back to here. Let's see what's happening. A transpose time x means A transpose time lambda x1 plus 1 minus lambda x2. And now take the scalar outside. This is x1. Take the scalar outside. This is x2. And now we know this is less than or equal. There we go, because of this, because x1 and x2 are visible solutions. We know that A transpose x1 is less than or equal B I, and A transpose x2 is less than or equal Pi also. So this is less than or equal Pi plus 1 minus lambda, and this is less than or equal Bi, and this is Bi, and then we are done. So we have achieved what we want from here to here. So this is achieved. Good. Now let's write what we have concluded. Given two visible solutions, then, or let me write it very briefly this way. Any point on the line segment. This is very important for us to work for linear programming problems for the next chapter. Any point on the line segment, which line segment? Joining two, I believe, joining two visible solutions is also a visible solution. And when we say visible solutions, mean a visible solution for some linear programming problem. So any point, on the line segment joining to visible solution is also a visible solution. Okay, good. This is very important for us. Very, very basic and very important. And above there is the proof. Now, if we go back to see, this constraint was less than or equal, right? Now, if we go back and make it equal, you know, less than or equal is for the standard form. The canonical form takes equality. So if we go back and change them all to equality, same thing will happen. Same process still apply. And we may change them to something different. We may change them to equality or less than or equal. So whatever of these, everywhere. And the proof will still work for any of these, okay? So either equality or greater than or equal, the proof is still working. Okay. Good. Now, if we have two visible solutions, then any point between them is a visible solution. If we have two visible solutions, then any point between them is a visible solution. That's I like that. So let me rewrite this again. This also means any point between. Oh, it isn't there. If we have two visible solutions, then the points, any point between them is a visible solution, without saying a line segment. It's okay. It is there. Now, good. So, what is the idea here? Now, we will prove that the objective function, you see, we have two visible solutions, and the line between them, all the points on the line are visible solutions. But the question now, the linear programming problem has an objective function. We will show that this objective function will take the maximum at either this end of the line segment or the other end. A maximum or a minimum will happen at the end point, not at any line on the line, any point on the line segment. Again, now we show that the objective function remember, objective function used to be given z equals c transpose x, right? Takes its maximum or minimum according to the question at an endpoint. So I will say takes I mean by takes minimum or maximum relatively to a segment. So if I have two visible solutions and I have a segment joining them, segment line, then I say the objective function will have the greatest value for all the points on that segment at the greatest value at one of the endpoints, or the minimum at one of the endpoints. Okay, so at an endpoint. How do we show that? It says, like, in other words, it says the value of the objective function at any point, interior point inside the line segment, is less than or equal the value, is between, actually, the value of the objective function at the endpoints. So, okay, so let me explain what I'm saying here. So let me draw a line. So we have visible solutions x1 and x2. Okay, assume for a while that Cx2, C transpose x2, which is the we're talking about the objective function, the value of that is bigger than the objective function at x1. Okay, so the objective function takes a bigger value at x1. Now, if we choose any point inside the line segment and call it x, then we will show that the objective function, the value of the objective function between this x, is less than or equal its value at x2, and greater than or equal its value at x1. Okay, and please don't let my graph confuse you because I'm drawing x2 higher. No, this is not the case. We might have like x1 here and x2 here, and same thing still apply, and x somewhere, and same thing here, same thing here still apply for that. My graph, second graph here, the value of the objective function at x2 still bigger the value of the objective function at x1. It does not matter where I plot x1 or x2. This is just a demonstration. Okay, so now this is what we are claiming. The value of the objective function at any line segment will be between the values of the objective functions at the endpoints. This is what we are claiming, and that proves what I wrote here. Now we show that the objective function takes its minimum or maximum at an endpoint. So the minimum and maximum will not be in the middle, right? Because the endpoints, the minimum and maximum happens at endpoints. This is what I have highlighted in yellow, and we want to prove it. Let us prove it. To prove this, okay. Right, x, so x is here on the line segment, so it equals lambda x1 plus 1 minus lambda x2 for some lambda between 0 and 1, right? Now, okay, C transpose x equals lambda C transpose x1 plus 1 minus lambda C transpose x2. Good? Okay. Now look what happened here. This here is less than or equal C2. So we will replace it. So this is lambda less than lambda C2 C transpose x2. So I replace C transpose x1 by C transpose x2. 1 minus lambda C transpose x2. But this together brings us to C transpose x2, right? Because I have lambda here and 1 minus lambda here multiplied by the same amount. So what I got here, that the objective function takes the value less than or equal C transpose x2. So I got this. Now I want to prove the other equality. What I do, I will work the same, but this time I will replace C transpose x2 by C transpose x1. What I mean, the following. Now again, C transpose x, I will write this again. C transpose x equals lambda C transpose x1 plus 1 minus lambda C transpose x2. Now we will replace this with C transpose x1, and this is why we get now 1 minus lambda C transpose x1. Now we have the same amount here, 1 time multiplied by lambda, other by 1 minus lambda. So this is C transpose x1. And so what we got, C transpose x1 is less than or equal C transpose x. And so we have proved that. So good. If we have two visible solutions, then the function will take a minimum or maximum on the endpoints. Good? This is what we want to show. How this will help us for later? Do you remember when we have drawn, say this is y, this is x-axis, okay, and this is z, and then we have such a constraint, okay, and then we took the closed half space, and then we have seen another constraint which looks like this, and then we take the half space of that constraint, and then what we have done is the following. Now this is our convex set here, the intersection of half spaces, okay. Now we are seeing here, now let us assume we have a plane above there, which is the objective function. I need to change the color. Assume we have an objective function drawn somewhere, which is a plane, right? Objective function is a plane. Now we want to find the minimum and maximum on the minimum and the maximum value on the plane corresponding to this area, okay. Actually, pay attention to this because this is the linear programming problem. So we want to know on this part of the plane, where is the minimum and the maximum it takes. If the plane is leaning this way, it looks at the origin. If the plane goes the other way, it looks at this corner maybe. Okay, this corner, okay. Now, because we have these to be visible solutions, now if you connect any two of them with a line segment, then you are sure that the objective function will take a value which is less than the value it takes at one of the points, making the line segment. For example, if we go here, from here to here, now for sure the maximum would be either here or either here. Now take another line, maybe from this one to this one, the line segment joining this one to this one. Then the minimum or maximum would be here or here. take this point or this point, the minimum or maximum here or here, okay? Take any line segment you want between these two corners. Now, we conclude that the maximum or the minimum will happen at one of these corners, okay? So the objective function, this is what we want to conclude. The objective function takes its maximum or minimum at a corner of the convex set. Which convex set? Which one? Which is the intersection of all the half spaces of all the closed half spaces corresponding to what? To the constraints of the linear programming problem. And highlight it the way you like. The objective function will take its minimum or maximum at the corner point. Corner point of what? Of the convex set. Which convex set? The one that comes as the intersection of closed half space. Which closed half space? The ones that came out of the constraints of the linear programming problem. Great. So this is the conclusion so far we have since the beginning. Let me say of this section. This is the conclusion of this section at least. So, and if anyone has any question, please go ahead. We are done for today. Thank you.